Listening practice, an expanded draft of the introduction section for your book, incorporating depth and actionable insights while maintaining clarity and flow. Introduction 1.1 The importance of practical principles in modern industries. In an era defined by rapid technological advancement, globalization, and resource constraints, industries face unprecedented challenges that demand solutions grounded in practicality. Practical principles rooted in efficiency, sustainability, and adaptability serve as the backbone of innovation. Whether in designing resilient infrastructure, optimizing supply chains, or managing cross-disciplinary teams, these principles ensure that theoretical knowledge is translated into tangible outcomes. For example, the construction industry's shift toward modular building techniques demonstrates how practical design principles reduce costs and environmental impact. In tech-driven fields like AI and robotics, iterative prototyping bridges the gap between theoretical models and real-world functionality. This section underscores how practical principles not only solve problems but also drive competitive advantage in sectors such as manufacturing, urban development, and digital services. 1.2 Bridging theory and practice. While academic research and theoretical frameworks provide critical foundations, their true value lies in application. This subsection explores strategies to close the gap between what we know and how we execute, case-based learning, integrating real-world scenarios into education and training programs, e.g., engineering simulations, business strategy workshops. Agile methodologies, emphasizing flexibility and rapid feedback loops to adapt theories to dynamic project needs. Collaborative ecosystems, fostering partnerships between academia, industry, and governments to align research with market demands, e.g., university-led R&D for sustainable materials. A case study on Tesla's gigafactories illustrates how theoretical advancements in battery technology are scaled into mass production through practical engineering and lean management. 1.3 Overview of key fields: design, analysis, construction, and management. This subsection introduces the 4 pillars of the book, highlighting their interdependence and unique roles in delivering successful outcomes. 1. Design, the creative process of solving problems through user-centric solutions, e.g., ergonomic product design, climate-responsive architecture. 2. Analysis, the systematic evaluation of data, risks, and feasibility to inform decisions, e.g., finite element analysis in engineering, SWOT analysis in business. 3. Construction, the physical, or digital, execution of plans, balancing precision, safety, and innovation, e.g., 3D printed buildings, smart city infrastructure. 4. Management, orchestrating resources, timelines, and teams to achieve objectives, e.g., critical path method in project management, stakeholder engagement in public works. The chapter concludes by framing these fields as interconnected components of a holistic workflow. For instance, a green energy project might involve designing solar panel layouts for maximum efficiency, analyzing environmental and financial impacts, constructing with sustainable materials and automated systems, managing regulatory compliance and community partnerships. Key themes to carry forward: interdisciplinarity. Success in modern industries requires blending insights from engineering, economics, social sciences, and technology. Sustainability, practical principles must prioritize long-term ecological and social resilience. Adaptability, techniques like AI-driven predictive analytics and agile workflows ensure systems evolve with changing demands. This introduction sets the stage for deeper dives into each field, emphasizing that practical principles are not static rules but dynamic tools for navigating complexity. Let me know if you'd like to refine any section further. Here's an expanded and detailed draft for Chapter 1.1, Foundational Design Principles, structured to provide depth, actionable insights, and real-world relevance. Chapter 1, Practical Principles in Design. 1.1 Foundational Design Principles. Design is the intersection of problem-solving and creativity, where principles act as guardrails to ensure solutions are effective, ethical, and enduring. This section unpacks the core tenets that define successful design across industries. Functionality, aesthetics, and sustainability. These three pillars form the bedrock of modern design, balancing technical rigor with human and environmental needs. 1. Functionality, definition, ensuring a design fulfills its intended purpose efficiently and reliably. Key considerations: ergonomics, usability, scalability, and adaptability. Example: IKEA's flat-pack furniture prioritizes ease of assembly, transport, and modularity without compromising utility. Actionable strategy: use user journey mapping to identify pain points and optimize functionality. 2. Aesthetics, definition, creating visually and emotionally resonant solutions that enhance user engagement. Key considerations: color theory, material textures, cultural symbolism, and brand alignment. Example: Apple's product design merges minimalist aesthetics with intuitive interfaces, fostering brand loyalty. Actionable strategy, apply Gestalt principles, e.g., proximity, symmetry, to create cohesive visual hierarchies. 3. Sustainability, definition, designing systems that minimize ecological harm and maximize long-term resource efficiency. Key considerations: life cycle analysis, circular economy principles, and low-carbon materials. Example: the Edge building in Amsterdam uses smart lighting, solar panels, and rainwater harvesting to achieve net zero energy use. Actionable strategy, integrate cradle-to-cradle, C2C, certification criteria into material selection. Interplay and trade-offs: a chair designed for a public space must be durable, functionality, visually inviting, aesthetics, and made from recyclable materials, sustainability. Challenge: balancing cost constraints with sustainable materials often requires innovative compromises, e.g., Adidas Parley shoes made from ocean plastic. Human-centered design, HCD, and user experience, UX. HCD and UX prioritize empathy and iterative feedback to create solutions that resonate with end users. 1. Human-centered design, HCD, framework, a 4-phase process: discover, define, develop, deliver that embeds user needs at every stage. Tools: empathy mapping to uncover user motivations and frustrations. CO creation workshops involving stakeholders in prototyping. Case study: OXO Good Grips kitchen tools revolutionized ergonomic design by involving arthritis patients in the design process. 2. User experience, UX, definition, crafting seamless, intuitive interactions between users and products/services. Key elements: accessibility, responsiveness, and emotional engagement. Example: Airbnb's platform simplifies booking through clean UI, personalized recommendations, and trust-building features, e.g., verified reviews. Actionable strategy: conduct A/B testing to refine features like button placement or checkout flows. Bridging HCD and UX, digital healthcare apps, combining HCD's focus on patient needs, e.g., Mysigra for diabetes management, with UX's emphasis on intuitive interfaces. Pitfalls to avoid: over-engineering features that users find overwhelming, e.g., cluttered dashboards. Case study spotlight, designing for accessibility project, Microsoft's Xbox Adaptive Controller, challenge, create a gaming controller for players with limited mobility. HCD/UX approach, partnered with gamers, occupational therapists, and NGOs to identify needs. Prioritized modularity, large programmable buttons, plug-and-play ports. Outcome: a landmark in inclusive design, praised for its functionality and empowering user experience. Key takeaways for practitioners: 1. Balance the triad. Functionality, aesthetics, and sustainability are non-negotiable in modern design. Neglecting one risks failure. 2. Empathy drives innovation. HCD and UX are not buzzwords but frameworks to uncover unmet needs, e.g., Tesla's touchscreen dashboards replacing traditional knobs. 3. Iterate relentlessly. Use prototypes, user testing, and feedback loops to refine designs, e.g., Dyson's 5,127 prototypes for its first vacuum. Design exercise, apply the principles. Scenario, redesign a public bus stop for a climate with extreme heat and high foot traffic. Steps, 1. Functionality, ensure shade, seating, and real-time transit updates. 2. Aesthetics, use reflective materials and vibrant art to uplift commuters. 3. Sustainability, incorporate solar panels and passive cooling. 4. HCD/UX, interview daily users to identify pain points, e.g., elderly passengers needing handrails. This section equips readers to translate principles into practice, emphasizing that great design is not about perfection but solving real problems with creativity and rigor. Let me know if you'd to dive deeper into any concept. Here's an expanded, structured draft for Chapter 1.2, Design Tools and Methodologies, Blending Theory, Practical Insights, and Real-World Applications. Chapter 1, Practical Principles in Design. 1.2 Design Tools and Methodologies. Modern design thrives on structured processes and cutting-edge tools that transform ideas into reality. This section explores iterative frameworks and technologies that enable efficiency, collaboration, and innovation. Iterative design processes. Iterative design emphasizes incremental development, continuous feedback, and adaptability. Two dominant methodologies are Agile and Lean, each with unique strengths. 1. Agile methodology, core philosophy, deliver value early and often through short, collaborative cycles, sprints. Key principles, user stories, define features from the end user's perspective, e.g., as a commuter, I need real-time bus updates. Sprint retrospectives, reflect on progress and adjust workflows. Case study, Spotify's squad model uses cross-functional teams, designers, developers, testers, to rapidly iterate on music recommendation algorithms. Actionable strategy, use Kanban boards, Trello, Jira, to visualize tasks and prioritize backlogs. 2. Lean design, core philosophy, eliminate waste, time, resources, effort, to focus on value-creating activities. Key principles, MVP, minimum viable product test. Core functionality with minimal features, e.g., Dropbox's initial video demo to gauge user interest, continuous improvement, Kaizen. Small, incremental changes over time. Case study, Toyota's lean production system reduced car assembly errors by empowering workers to halt production and fix issues immediately. Actionable strategy, conduct value stream mapping to identify and remove bottlenecks in workflows. Agile versus Lean, Agile excels in software and dynamic environments requiring flexibility. Lean suits manufacturing and processes where efficiency is paramount. Hybrid approach, Lean Agile combines speed with waste reduction, e.g., Tesla's rapid prototyping paired with just-in-time part delivery. Software and prototyping tools. Advanced tools streamline design workflows, enabling precision, collaboration, and rapid iteration. 1. Computer-aided design, CAD, purpose, create 2D/3D models for engineering, architecture, and product design. Tools, AutoCAD, SolidWorks, Fusion 360. Applications, automotive design, Tesla uses CAD to simulate aerodynamics and crash tests. Fashion, CAD software like CLO3D enables virtual garment prototyping. Actionable strategy, use parametric modeling to automate design adjustments, e.g., resizing a gear based on load requirements. 2. Building information modeling, BIM, purpose, collaborative 3D modeling for architecture, engineering, and construction, AEC. Tools, Revit, ArchiCAD, Navisworks. Applications, clash detection, identify conflicts between electrical and plumbing systems before construction. Life cycle management, track maintenance schedules and energy use, e.g., the Shard in London. Case study, BIM in the Sydney Opera House renovation reduced rework costs by 20% through precise digital coordination. 3. 3D modeling and prototyping, purpose, visualize concepts and test functionality through physical/digital prototypes. Tools, digital, Blender, SketchUp, Rhino. Physical, 3D printers, Formlabs, CNC machines. Applications, healthcare, 3D printed prosthetics tailored to patient anatomy, e.g., Open Bionics Hero Arm. Consumer products, Dyson's 3D printed prototypes accelerated vacuum cleaner development. Actionable strategy, combine rapid prototyping with user testing to validate designs early, e.g., Figma for UI/UX mockups. Integrating tools and methodologies. A cohesive workflow merges processes and tools for maximum impact. 1. Agile and CAD. Automotive teams use sprints to refine CAD models based on weekly stakeholder feedback. 2. Lean and BIM. Construction firms apply BIM to minimize material waste and rework, aligning with Lean's waste reduction goals. 3. 3D printing and MVP. Startups 3D print MVP prototypes to test market viability before mass production. Example, Philips Healthcare Division uses Agile sprints, CAD simulations, and 3D printed prototypes to design MRI machines that reduce patient claustrophobia. Pitfalls to avoid. 1. Tool overload, adopting too many tools without mastering workflows, e.g., juggling Revit, AutoCAD, and SketchUp simultaneously. 2. Ignoring feedback, treating iterations as a checkbox exercise rather than a learning opportunity. 3. Siloed teams, failing to integrate designers, engineers, and managers into collaborative platforms like BIM 360. Design exercise, build a smart home device. Scenario, design a voice-controlled thermostat for elderly users. Steps. 1. Agile sprints, break tasks into 2-week cycles, e.g., week 1, UX flow, week 2, prototype. 2. CAD/BIM, model the device in Fusion 360, ensuring ergonomic buttons and clear displays. 3. 3D print, create a tactile prototype for usability testing. 4. Lean feedback, iterate based on elder focus groups to simplify voice commands. Emerging trends, generative design, AI-powered tools, e.g., Autodesk Generative Design, create optimized structures based on input parameters. Digital twins, virtual replicas of physical systems, e.g., Siemens MindSphere, enable real-time performance monitoring. AR/VR prototyping, tools like Unity and Unreal Engine allow immersive design reviews, e.g., architects walking through unbuilt spaces. Key takeaways for practitioners. 1. Match methodology to context, Agile for flexibility, Lean for efficiency. 2. Leverage tools strategically, CAD/BIM for precision, 3D modeling for rapid validation. 3. Collaborate early, break silos with shared platforms, e.g., BIM 360, Figma. 4. Embrace hybrid workflows, combine iterative processes with emerging tech, AI, AR, to stay competitive. This section bridges theory and practice, equipping readers to select and integrate tools/methodologies that align with project goals, budgets, and timelines. Let me know if you'd like to explore specific tools or case studies in more depth. Here's an expanded, detailed draft for Chapter 1.3, Case Studies in Applied Design, structured to showcase real-world applications of design principles, tools, and methodologies across diverse fields. Chapter 1, Practical Principles in Design. 1.3 Case Studies in Applied Design. This section highlights how foundational principles, iterative processes, and advanced tools converge to solve complex challenges. Each case study demonstrates the interplay of functionality, aesthetics, sustainability, and human-centered design. Case Study 1, Urban Infrastructure Design Project, The High Line, New York City Challenge, transform a derelict elevated railway into a public space that revitalizes the neighborhood while preserving historical essence. Design principles applied. 1. Functionality, repurposed rail tracks into walkable pathways with seating, greenery, and sight lines. Integrated accessibility features, elevators, ramps, for universal access. 2. Aesthetics, blended industrial remnants, exposed rails, with natural landscaping, wildflowers, native plants. Commissioned site-specific art installations to reflect local culture. 3. Sustainability, stormwater management using permeable paving and self-sustaining plantings. Reduced urban heat island effect through green corridors. Tools and methodologies, BIM, coordinated multidisciplinary teams, architects, engineers, ecologists. Community engagement, workshops with residents to align design with neighborhood needs. Outcome, increased property values by 103% in adjacent areas. Hosts 8 million visitors annually, becoming a blueprint for adaptive reuse, e.g., Seoul's Sky Garden. Key takeaway, urban design thrives when balancing heritage preservation, ecological stewardship, and community inclusivity. Case Study 2, Product Design for Accessibility Project, Microsoft Xbox Adaptive Controller Challenge, create an affordable, customizable gaming controller for players with limited mobility. Design Principles Applied, 1. Human-Centered Design, HCD, collaborated with gamers, occupational therapists, and NGOs, e.g., Able Gamers, to identify pain points, prioritized modularity, large programmable buttons, 19 plug-and-play ports for external switches. 2. Aesthetics, sleek, minimalist design to avoid stigmatization. Tactile surfaces and high-contrast labels for low-vision users. Tools and methodologies, 3D prototyping, rapid iterations tested with users to refine ergonomics. Agile development, weekly feedback loops with beta testers. Outcome, praised as a landmark in inclusive design, winning the 2019 Design Museum's Beasley Design of the Year. Inspired competitors like Sony's Project Leonardo, broadening industry standards. Key takeaway, accessibility isn't a niche, it's an innovation catalyst that benefits all users, e.g., curb cuts originally designed for wheelchairs now aid cyclists. Case Study 3, Sustainable Architectural Solutions Project, Bosco Verticale, Vertical Forest, Milan Challenge, combat urban pollution through architecture while creating livable, biodiverse spaces. Design Principles Applied, 1. Sustainability, 20,000 plants and 900 trees absorb 30 tons of CO annually. Gray water recycling and solar panels reduce energy use by 40%. 2. Functionality, balconies designed with reinforced concrete to support tree roots and wind loads. Automated irrigation system powered by renewable energy. 3. Aesthetics, seasonal color shifts, blooming flowers in spring, evergreen foliage in winter, create a dynamic facade. Tools and methodologies, parametric modeling, optimized tree placement for sunlight and structural load. Life cycle assessment, LCA evaluated material sustainability, e.g., recycled concrete. Outcome, reduced particulate matter by 20% in surrounding areas. Inspired global replicas, e.g., Nanjing Vertical Forest. Key takeaway, sustainable architecture must harmonize ecological impact with human well-being. Green spaces aren't just nice to have but critical for urban resilience. Cross-case insights. 1. Interdisciplinary collaboration, all projects required input from ecologists, engineers, and end users. 2. Iteration as a necessity, the High Line underwent 1,000 plus design revisions, Xbox controller had 15 prototype versions. 3. Scalability, solutions like Bosco Verticale's green facades are now modular systems for retrofitting older buildings. Design exercise, redesign a public library scenario, create a library that is accessible, sustainable, and culturally resonant. Steps, 1. Research, conduct community surveys to identify needs, e.g., quiet zones, multilingual resources. 2. HCD, partner with disability advocates to design tactile navigation for visually impaired users. 3. Sustainability, use reclaimed materials, solar canopies, and green roofs. 4. Prototype, develop a BIM model to simulate energy use and user flow. Emerging trends in applied design, biophilic design, integrating nature into urban spaces, e.g., Singapore's Jewel Changi Airport. AI-driven customization, tools like Autodesk Dreamcatcher generate design options based on user input. Circular design, IKEA's buyback program refurbishes used furniture for resale. Key takeaways for practitioners. 1. Start with empathy. Solutions fail when users aren't involved early, e.g., the Xbox controller's CO creation model. 2. Measure impact, quantify sustainability, CO reduction, and inclusivity, user satisfaction scores. 3. Scale thoughtfully, adapt successful models, highline, to local contexts without replicating blindly. This section reinforces that design is never static, it's a responsive, evolving practice where principles meet pragmatism. Let me know if you'd like to explore additional case studies or dive deeper into specific tools. Chapter 2, Analytical Frameworks for Decision-Making. 2.1 Principles of Effective Analysis. Effective analysis bridges raw data and actionable insights, enabling organizations to navigate complexity with clarity. This section explores two pillars of modern analysis: data-driven decision-making and risk assessment and mitigation, emphasizing their interplay in fostering resilient strategies. Data-driven decision-making definition: the practice of basing decisions on empirical data rather than intuition, reducing bias and enhancing objectivity. Key principles: 1. Holistic data integration, combine structured, sales figures, surveys, and unstructured data, social media sentiment, customer feedback. 2. Iterative process, collect, use IoT sensors, CRM systems, or surveys. Analyze, apply statistical models, regression, clustering, or machine learning. Interpret, contextualize results with domain expertise. Act, implement changes and monitor outcomes. 3. Tools and technologies, BI tools, Tableau, Power BI. Advanced analytics, Python, Pandas, scikit-learn, R, big data platforms, Hadoop, Snowflake. Case study: Amazon's dynamic pricing challenge, optimize prices in real time across millions of products. Approach: machine learning algorithms analyze competitor pricing, demand trends, and inventory levels. Outcome: increased margins by 10-25% while maintaining competitiveness. Challenges and solutions: data quality, implement automated validation checks, e.g., outlier detection. Siloed data, use integrated platforms like Salesforce or SAP. Ethical risks, audit algorithms for bias, e.g., racial/gender disparities in loan approvals. Key takeaway: data is a compass, not a map. Human judgment remains critical to contextualize insights. Risk assessment and mitigation strategies. Definition: identifying, evaluating, and addressing uncertainties that threaten organizational objectives. Key principles: 1. Risk identification, internal, operational inefficiencies, talent gaps. External, market shifts, regulatory changes, geopolitical instability. 2. Assessment methods, qualitative, SWOT analysis, risk matrices, likelihood versus impact. Quantitative, Monte Carlo simulations, value at risk, VAR. 3. Mitigation strategies, avoid, exit high-risk markets, e.g., Uber's withdrawal from China. Transfer, insurance, outsourcing, e.g., cloud security via AWS. Mitigate, redundant systems, diversification, e.g., Toyota's multi-supplier strategy post-2011 tsunami. Accept, budget for contingencies, e.g., construction project buffers. Case study: JP Morgan Chase's credit risk modeling challenge, predict loan default probabilities accurately. Approach: machine learning models analyze credit history, spending patterns, and macroeconomic indicators. Outcome: reduce default rates by 15% while expanding access to credit. Emerging trends, AI-driven risk prediction, tools like Palantir forecast supply chain disruptions. Scenario planning, stress testing for black swan events, e.g., COVID-19. Challenges and solutions, overconfidence in models, pair quantitative analysis with expert panels. Dynamic risks, implement real-time monitoring, e.g., cybersecurity threat detection. Key takeaway, proactive risk management transforms threats into opportunities for innovation. Synergy between data and risk, predictive analytics, retailers like Walmart use sales data to anticipate supply chain bottlenecks. Risk-aware culture, Google's pre-mortem exercises simulate project failures to preempt risks. Design exercise, optimize a retail supply chain scenario, a fashion retailer faces stockouts and overstock issues. Steps, 1. Data collection, gather historical sales, supplier lead times, and social media trends. 2. Risk assessment, identify risks, e.g., shipping delays, demand volatility. 3. Mitigation plan, use predictive analytics to adjust inventory levels. Diversify suppliers to avoid single points of failure. Key takeaways for practitioners. 1. Balance data and judgment, avoid analysis paralysis by setting decision thresholds, e.g., 80% confidence. 2. Embed risk thinking, integrate risk assessments into daily workflows, not just annual reviews. 3. Leverage technology, automate data pipelines and risk alerts to stay agile. This section equips readers to harness data and risk frameworks as complementary tools, fostering decisions that are both informed and resilient. Let me know if you'd like to explore specific industries, e.g., healthcare, fintech, or advanced techniques. Chapter 2, Analytical Frameworks for Decision-Making 2.2 Tools for Technical and Business Analysis. This section explores critical tools for technical and business analysis, emphasizing their role in bridging engineering rigor and economic/environmental sustainability. Structural analysis, finite element analysis, FEA, and computational fluid dynamics, CFD. 1. Finite element analysis, FEA, definition, a computational method to predict how structures respond to forces, vibration, heat, and other physical effects. Applications, aerospace, stress testing airplane wings for fatigue resistance, e.g., Boeing 787 Dreamliner. Automotive, crash simulation to optimize vehicle safety. Tools, ANSI, Abacus, SolidWorks simulation. Case study, Tesla's battery pack design, challenge, ensure structural integrity under thermal and mechanical stress. Process, via modeled heat dissipation and impact resistance, leading to a honeycomb design that reduced weight by 15%. 2. Computational fluid dynamics, CFD, definition, simulates fluid flow, heat transfer, and chemical reactions to optimize system performance. Applications, energy, wind turbine blade design for maximum efficiency. Healthcare, modeling blood flow in artificial heart valves. Tools, COMSOL Multiphysics, OpenFOAM, Autodesk CFD. Case study, Formula 1 aerodynamics, challenge, minimize drag while maximizing downforce. Process, CFD simulations refined front/rear wing designs, improving lap times by 1.5 seconds. Challenges and mitigations, over-reliance on simulations, validate with physical prototypes, e.g., wind tunnel testing. Computational costs, use cloud-based solutions, AWS, Azure HPC, for scalability. Synergy with business tools, FEA/CFD data informs life cycle costs, e.g., material selection and risk assessments, e.g., failure probability. Business analysis, cost-benefit analysis, CBA, and life cycle assessment, LCA. 1. Cost-benefit analysis, CBA, purpose, quantify financial viability by comparing total costs and benefits. Steps: 1. Identify costs, direct, materials, labor, and indirect, training, downtime. 2. Quantify benefits, revenue growth, risk reduction, brand equity. 3. Discount future values, adjust for time value of money. Tools: Excel, Palisade at Risk, SAP Analytics. Case study: High-Speed Rail Project, CBA outcome, projected $2.1 billion net benefit over 30 years, viaduct reduced congestion and emissions. 2. Life Cycle Assessment, LCA, purpose: evaluate environmental impact from cradle to grave, raw materials to disposal. Phases: 1. Inventory analysis, track energy use, emissions, waste. 2. Impact assessment, convert data into ecological metrics, e.g., CO equivalents. 3. Interpretation, identify hotspots for improvement. Tools: CIMAPro, Gabi, OpenLCA. Case study: Patagonia's recycled polyester, LCA insight, switching to recycled materials reduced CO emissions by 35% compared to virgin polyester. Challenges and mitigations: data gaps, use industry databases, EcoInvent, for standardized metrics. Complexity, simplify with modular LCA frameworks. Integration with technical tools, CBA/LCA leverage FIA/CFD outputs, e.g., material efficiency, to assess economic and environmental trade-offs. Cross-functional case study, electric vehicle, EV, development scenario, designing an affordable, sustainable EV. 1. Technical analysis, FIA, optimize battery casing for crash safety. CFD, reduce aerodynamic drag to extend range. 2. Business analysis, CBA, compare lithium-ion versus solid-state battery costs. LCA, assess mining impacts of lithium versus recyclability of aluminum. Outcome, a competitively priced EV with 20% lower life cycle emissions than rivals. Key takeaways for practitioners: 1. Complementary tools, pair FIA/CFD with CBA/LCA to balance performance, cost, and sustainability. 2. Iterate early, run simulations and LCAs during prototyping to avoid costly redesigns. 3. Stakeholder alignment, translate technical jargon into business metrics, e.g., ROI, carbon footprint, for cross-departmental buy-in. Design exercise, green building retrofit scenario, upgrade an office building for energy efficiency. Steps: 1. CFD, model airflow to optimize HVAC placement. 2. FIA, assess roof strength for solar panel installation. 3. CBA, compare insulation materials, cost versus energy savings. 4. LCA, evaluate solar panels' life cycle emissions versus grid reliance. This section equips readers to leverage technical and business tools in tandem, ensuring decisions are innovative, economically sound, and environmentally responsible. Let me know if you'd like to explore sector-specific applications, e.g., renewable energy, consumer goods. Chapter 2, Analytical Frameworks for Decision-Making 2.3 Case Studies in Analysis. This section illustrates how analytical tools and frameworks resolve real-world challenges in supply chain optimization and environmental sustainability. Each case study emphasizes data-driven decision-making, risk assessment, and interdisciplinary collaboration. Case Study 1, Optimizing Supply Chains in Manufacturing Project, Toyota's post-2011 Tsunami Supply Chain Resilience Challenge, rebuild a global supply chain disrupted by the Tohoku earthquake, which halted production of 150-plus critical components. Analytical approach: 1. Risk mapping, identified single-source suppliers and prioritized multi-sourcing for high-risk parts. 2. Simulation modeling, used digital twins to simulate disruptions and test recovery strategies. Implemented network optimization software, LlamaSoft, to reroute logistics. 3. Predictive analytics, Forecasted supplier lead times and inventory needs using AI-driven tools. Outcomes: reduced dependency on single suppliers by 40%. Achieved 98% supply chain recovery within 6 months. Established a resilience index to monitor supplier risk in real time. Key takeaway: proactive risk analysis and diversification are critical to mitigating supply chain vulnerabilities. Case Study 2, Environmental Impact Analysis for Renewable Energy Projects. Project, Hornsea Project 1 Offshore Wind Farm, UK. Challenge: balance renewable energy goals with ecological preservation in the North Sea. Analytical approach: 1. Environmental impact assessment, EIA, GIS mapping, tracked migratory bird routes and marine mammal habitats. Habitat suitability models, predicted impacts on species like the red-throated diver. 2. Life cycle assessment, LCA evaluated carbon footprint from construction to decommissioning. 3. Stakeholder analysis, engaged fishermen, NGOs, and coastal communities to address concerns. Mitigation strategies, seasonal restrictions on pile driving to avoid disrupting breeding cycles. Artificial reef installations to promote marine biodiversity. Outcomes: 1.2 GW capacity, powering 1 million homes with 30% lower CO emissions than fossil fuels. 1% decline in local bird populations, below projected thresholds. Key takeaway: holistic environmental analysis ensures renewable projects align with ecological and social priorities. Cross-case insights. 1. Data integration: both cases relied on merging real-time data, supplier logs, wildlife tracking, with predictive models. 2. Stakeholder collaboration: Toyota involved Tier 2 suppliers in risk planning, Hornsea included local communities in EIA revisions. 3. Adaptive frameworks: continuous monitoring allowed iterative improvements, e.g., Toyota's Resilience Index, Hornsea's Adaptive Marine Management. Design exercise: sustainable apparel supply chain scenario, a fashion brand aims to reduce carbon emissions by 50% while avoiding labor violations. Steps: 1. Supply chain analysis, audit suppliers using blockchain for transparency. 2. LCA, compare organic cotton versus recycled polyester emissions. 3. Risk assessment, flag regions with high labor risks via AI sentiment analysis of worker feedback. Emerging trends, AI for circular supply chains. IBM's AI-driven material recovery identifies recyclable components in e-waste. Biodiversity net gain, BNG UK mandates developers to achieve 10% BNG, spurring tools like Biodiversity Metric 4.0. Key takeaways for practitioners. 1. Leverage hybrid models, combine quantitative tools, simulations, with qualitative insights, stakeholder feedback. 2. Plan for uncertainty, build flexible frameworks to adapt to black swan events, climate disasters, policy shifts. 3. Measure beyond profit, integrate environmental and social metrics, CO, labor equity, into core KPIs. This section underscores that effective analysis is not just about solving problems, it's about anticipating them. By marrying technical rigor with ethical foresight, organizations can turn analytical insights into enduring value. Chapter 3, Construction Principles and Best Practices. 3.1 Core Principles of Modern Construction. Modern construction demands a harmonious blend of safety, compliance, efficiency, and sustainability. This section explores two foundational pillars: safety protocols and regulatory compliance, and resource efficiency and waste reduction, highlighting their interplay and practical applications. Safety protocols and regulatory compliance. 1. Safety protocols, personal protective equipment, PPE. Mandatory use of helmets, gloves, harnesses, and high-visibility clothing to mitigate injuries. Training programs, regular workshops on hazard recognition, e.g., fall risks, electrical safety, and emergency response, fire drills, first aid. Technology integration, wearables, smart helmets with sensors to monitor fatigue or environmental hazards. Drones, conduct aerial inspections of hard-to-reach areas, reducing worker exposure to risks. Case study, Crossrail Project, London, implemented a safety ambassador program, reducing incidents by 35% through peer-led training and real-time hazard reporting apps. 2. Regulatory compliance, key standards, OSHA, U.S. enforces workplace safety, including scaffold stability and excavation safeguards. ISO 45001, Global Standard for Occupational Health and Safety Management Systems. Certifications, LEED and BREEAM require compliance with safety and environmental benchmarks. Regional variations, EU CE marking versus US ANSI standards for material safety. Challenges and solutions, subcontractor compliance, centralized digital platforms, e.g., Procore, to track certifications and training across teams. Evolving regulations, AI tools like SiteAware scan legal updates and alert teams to new requirements. Resource efficiency and waste reduction. 1. Resource efficiency, material optimization, BIM, building information modeling reduces design errors and material over-ordering, e.g., Skanska saved 20% on steel via BIM precision. Modular construction, prefabricated components cut on-site waste and speed up timelines. Sustainable materials, recycled steel, low-carbon concrete, and cross-laminated timber, CLT. Case study, The Edge, Amsterdam used 100% recycled aluminum facades and achieved 98% material reuse during renovations. 2. Waste reduction, lean construction principles, just-in-time delivery, minimizes storage needs and material degradation, e.g., Toyota's model in construction. Waste hierarchy, prioritize reuse, e.g., repurposing excavation soil, over recycling. Circular economy, zero waste goals, the Bullitt Center, Seattle, diverted 96% of construction waste from landfills. Material passports, digital records enabling future disassembly and reuse, e.g., Modestur platform. Challenges and solutions, cost barriers, tax incentives for sustainable materials, e.g., US EPA's repowering program. Behavioral resistance, gamification apps, e.g., Planetly, reward teams for waste reduction milestones. Synergy between safety and sustainability, prefabrication, reduces on-site hazards, fewer workers, and waste, factory-controlled precision. Smart sensors, monitor both structural integrity, safety, and resource usage, efficiency, in real time. Case study, The Eden Project, UK, challenge, build a biodome complex with minimal environmental impact and zero fatalities. Approach, safety, rigorous PPE protocols and 360 degrees VR training for working at heights. Resource efficiency, locally sourced recycled materials and rainwater harvesting systems. Outcome, zero fatalities and 85% waste diversion rate. Became a global benchmark for eco-conscious construction. Key takeaways for practitioners. 1. Integrate early, embed safety and sustainability in design phases via tools like BIM. 2. Leverage technology, AI, IoT, and drones bridge compliance monitoring and efficiency gains. 3. Collaborate, engage suppliers, regulators, and communities to align goals, e.g., shared waste management hubs. Design exercise, high-rise retrofit scenario, upgrade a 1980s office tower for energy efficiency and seismic safety. Steps, 1. Safety audit, use drones to inspect facades and identify asbestos. 2. Resource plan, opt for CLT panels, low waste, and solar glass, energy efficiency. 3. Waste strategy, partner with local recyclers to repurpose demolition debris. This section underscores that modern construction thrives when safety, compliance, and sustainability are not competing priorities but interconnected pillars. By adopting these principles, projects can achieve resilience, cost savings, and lasting positive impact. Chapter 3, Construction Principles and Best Practices 3.2 Advanced Construction Techniques. Modern construction is undergoing a revolution driven by innovation, speed, and sustainability. This section explores two transformative approaches: modular/prefabricated construction and smart technologies, and their role in redefining efficiency, safety, and scalability. Modular and prefabricated construction definition: manufacturing building components off-site in controlled factory environments, then assembling them on-site. Types of prefabrication: 1. Volumetric modular, fully finished 3D units, e.g., bathroom pods, hotel rooms. 2. Panelized systems, wall, floor, or roof panels assembled on-site. 3. Hybrid, combines modular units with traditional construction, e.g., modular cores in high-rises. Benefits: speed, reduces project timelines by 30–50%, e.g., broad sustainable building erected a 57-story skyscraper in 19 days. Quality control, factory precision minimizes defects, e.g., Caterpillar's automated timber framing. Waste reduction, up to 90% less waste via optimized material usage. Safety, fewer on-site workers and hazards, e.g., reduced fall risks. Case study: Marriott's modular hotel rooms. Challenge: meet rising demand for affordable, consistent hotel spaces. Solution: factory-built rooms with integrated plumbing, electrical, and furnishings. Outcome: 25% faster construction and 15% cost savings per room. Challenges and solutions: logistics, use BIM for precise transportation planning, e.g., Skanska's modular hospital units. Design rigidity, design for disassembly, DFD, to allow future modifications. Smart technologies, IoT, robotics, drones. 1. Internet of Things, IoT, applications, smart sensors, monitor structural health, vibrations, cracks, in real time, e.g., Siemens IoT-enabled bridges. Wearables, track worker vitals, fatigue, heat stress, and alert supervisors. Equipment tracking, RFID tags on tools/materials reduce theft and loss. Tools, Autodesk BIM 360, Samsung SmartThings. 2. Robotics, types, bricklaying robots, SAM100 lays 3,000 bricks/day, versus 500 manually. 3D printing, Icon's Vulcan printer builds hurricane-resistant homes in 24 hours. Demolition robots, Brock's remote-controlled machines reduce hazardous manual labor. Case study: Foster and Partners Droneport in Rwanda. Goal: construct a drone delivery hub using local materials and robotic earth moving. Outcome: 90% reduction in manual excavation labor. 3. Drones, applications, surveying, LiDAR-equipped drones map terrain 10x faster than traditional methods. Inspections, thermal imaging drones detect HVAC leaks or insulation gaps. Progress monitoring, daily aerial updates for stakeholder transparency. Tools, DJI Phantom 4 RTK, drone deploy. Synergy example: smart highway construction, IoT sensors, monitor concrete curing and traffic flow. Robotic pavers, lay asphalt with millimeter precision. Drones, inspect road quality and track progress. Key challenges and mitigations. 1. High initial costs. Solution: lease modular factories or robotics as a service, RaaS, models. 2. Skill gaps. Solution: partner with vocational schools, e.g., Caterpillar's operator training simulators. 3. Regulatory hurdles. Solution: advocate for updated codes, e.g., Singapore's approval of 3D printed housing. Emerging trends, AI-driven modular design, algorithms optimize floor plans for prefab efficiency, e.g., Autodesk generative design. Swarm robotics, teams of drones/robots collaborate on large sites, e.g., Zurich's flying constructors. Digital twins, virtual replicas of buildings sync with IoT data for predictive maintenance. Design exercise, smart school construction scenario, build a net zero energy school in a remote area. Steps, 1. Modular design, prefab classrooms with integrated solar panels and insulation. 2. Robotics, deploy 3D printers for on-site concrete foundations. 3. IoT/drones, install moisture sensors in walls, use drones to monitor solar panel efficiency. Key takeaways for practitioners. 1. Start small, pilot modular or robotic techniques on low-risk projects, e.g., warehouses. 2. Collaborate early, involve manufacturers and tech providers during design. 3. Measure ROI, track time savings, waste reduction, and safety improvements to justify investments. This section illustrates how advanced techniques are not futuristic concepts but present-day tools reshaping construction. By embracing modular precision and smart technologies, the industry can build faster, safer, and greener, meeting the demands of a rapidly evolving world. Chapter 3, Construction Principles and Best Practices. 3.3 Case Studies in Construction. This section examines real-world applications of modern construction principles, showcasing how speed, safety, and sustainability are balanced in high-stakes projects and green-certified developments. Case Study 1, High-Rise Building Projects Balancing Speed and Safety Project, Salesforce Tower, San Francisco Challenge. Construct a 61-story, 1,070-foot skyscraper in a seismically active zone while adhering to aggressive timelines and zero-fatality safety goals. Approach, 1. Speed optimization, modular MEP systems, prefabricated mechanical, electrical, and plumbing units were assembled off-site, cutting installation time by 40%. Jump lift technology, hydraulic elevators moved materials upward as floors were completed, avoiding crane bottlenecks. 2. Safety innovations, damping system, a tuned mass damper and base isolators reduced seismic risk. IoT safety monitoring, wearables tracked worker vitals, while drones inspected facade integrity. 3. Collaborative workflows, BIM coordination, clash detection resolved design conflicts before construction, preventing delays. Daily safety huddles, crews reviewed hazards and progress in 15-minute meetings. Outcomes, completed in 4.5 years, 1.5 years faster than comparable projects. 0 fatalities and a 60% reduction in recordable incidents versus industry averages. LEED Platinum certification for energy efficiency. Key takeaway, speed and safety are not mutually exclusive. Modular methods, technology, and proactive planning enable both. Case Study 2, Green Building Certification, LEED, BREEAM, in Practice Project, 1 Angel Square, Manchester, UK, BREEAM Outstanding, Challenge, design Europe's largest BREEAM Outstanding office building with net zero carbon operations. Sustainable strategies, 1 Energy efficiency, tri-generation plant, combined cooling, heat, and power, CCHP, using rapeseed oil cut energy use by 50%. Double skin facade, reduced HVAC loads via natural ventilation and solar shading. 2 Resource management, rainwater harvesting, collected 100% of roof runoff for irrigation and toilets. Circular materials, 95% of demolition waste from the prior site was reused. 3 Biodiversity, green roofs, native plants supported pollinators and reduced stormwater runoff. Certification highlights, BREEAM score, 95.16%, highest ever for an office building at the time. Carbon savings, 80% reduction in operational carbon versus traditional offices. Outcomes, energy costs reduced by £200,000 annually. Won the 2014 REBA Sustainability Award. Key takeaway, green certifications like BREEAM and LEED drive innovation by setting measurable benchmarks for sustainability. Cross-case insights. 1. Technology as an enabler, both projects relied on BIM and IoT to harmonize speed, safety, and sustainability. 2. Holistic planning, early integration of green principles, e.g., 1 Angel Square CCHP system, avoids costly retrofits. 3. Stakeholder alignment, Salesforce Towers daily huddles and 1 Angel Square's contractor sustainability training fostered shared accountability. Design exercise, net zero residential tower scenario, build a 50-story residential tower in a dense urban area targeting LEED Platinum and minimal construction waste. Steps, 1 Modular design, precast facade panels with integrated insulation and solar cladding. 2 Safety tech, AI-powered cameras to detect unsafe behavior, e.g., missing harnesses. 3 Circular economy, partner with local recyclers to repurpose excavation waste into concrete aggregate. Emerging trends, smart buildings, IoT sensors optimize energy use post-occupancy, e.g., The Edge, Amsterdam. Carbon neutral certifications, new frameworks like LEED Zero and BREEAM Carbon target full life cycle emissions. Key takeaways for practitioners. 1. Certifications as roadmaps, LEED/BREEAM provide structured pathways to sustainability but require early commitment. 2. Speed is not equal to compromise, prefabrication and digital tools accelerate timelines without sacrificing safety or quality. 3. Measure and iterate, use post-occupancy data, energy use, occupant feedback, to refine future projects. This section underscores that modern construction is no longer about choosing between speed, safety, or sustainability. It's about integrating all three through innovation, collaboration, and relentless focus on outcomes. Chapter 4, Management Strategies for Execution and Oversight. 4.1 Principles of Effective Project Management. Effective project management hinges on selecting the right methodologies and fostering robust stakeholder relationships. This section explores Agile versus Waterfall methodologies and strategies for stakeholder communication and conflict resolution, offering actionable insights for balancing flexibility, structure, and collaboration. Agile versus Waterfall methodologies. Definitions and key principles. 1. Agile methodology, core philosophy, iterative, incremental delivery with flexibility to adapt to changing requirements. Key principles, sprints, short development cycles, 2-4 weeks, producing functional deliverables. Continuous feedback, regular stakeholder reviews, e.g., daily stand-ups, sprint retrospectives. Cross-functional teams, developers, designers, and testers collaborate closely. Tools, Jira, Trello, Scrum boards. 2. Waterfall methodology, core philosophy, linear, sequential phases, requirements design implementation testing deployment. Key principles, fixed scope, requirements defined upfront with minimal changes. Documentation driven, detailed plans and specifications before execution. Phase gates, progress only after formal approval of each phase. Tools, Gantt charts, Microsoft Project. Case studies, Agile in action, Spotify's squad model, challenge, rapidly innovate music recommendation algorithms in a dynamic market. Approach, autonomous squads iterated features in 2-week sprints, with user feedback shaping priorities. Outcome, reduced time to market by 30% and improved user engagement by 20%. Waterfall in action, Sydney Opera House construction, challenge, build an iconic structure with complex engineering requirements. Approach, sequential phases, design approval foundation roof shells, with strict milestone tracking. Outcome, delivered a landmark project, though delays and budget overruns highlighted Waterfall's rigidity. Comparison and hybrid approaches. Aspect Agile Waterfall flexibility high, adapts to changes, low, fixed scope, risk management early issue detection via iterations risks addressed in planning phase best for software, R&D, dynamic environments construction, regulated industries, e.g., pharma, drawbacks scope creep, requires stakeholder involvement inflexible to changes, late testing hybrid example, NASA's Artemis program, combines waterfalls phased approvals for rocket design with agile sprints for software systems. Actionable strategies, choose agile when requirements are unclear, innovation is critical, or rapid prototyping is needed. Choose waterfall when regulatory compliance, fixed budgets, or physical deliverables dominate. Hybrid tips, use agile for software components and waterfall for hardware in mixed projects. Stakeholder communication and conflict resolution key principles 1. Stakeholder identification, RACI matrix, clarify who is responsible, accountable, consulted, and informed. Power interest grid, prioritize engagement based on influence and interest. 2. Communication strategies, regular updates, weekly status reports, dashboards, e.g., Power BI and town halls. Tailored messaging, technical details for engineers, high-level summaries for executives. Tools, Slack, Microsoft Teams, Asana for transparency. 3. Conflict resolution, Thomas Gilman model, collaborating, win-win solutions, e.g., aligning team and client goals. Compromising, partial concessions, e.g., adjusting timelines to meet budget. Mediation, neutral third parties resolve disputes, common in public infrastructure projects. Case study, Boeing 787 Dreamliner, conflict, suppliers versus Boeing over design changes and delivery delays. Resolution, collaborative workshops, joint problem-solving sessions with suppliers. Transparent tracking, shared digital platforms for real-time progress updates. Outcome, restored trust and streamlined production after 3-year delays. Challenges and solutions, misaligned incentives, align KPIs across stakeholders, e.g., bonus structures tied to collective milestones. Cultural barriers, cross-cultural training for global teams, e.g., Toyota's Nemawashi consensus building. Resistance to change, pilot small wins to demonstrate benefits, e.g., agile trial in a low-risk project. Cross-methodology insights, agile stakeholder edge, daily stand-ups and sprint reviews keep stakeholders engaged. Waterfalls clarity, clear phase gates reduce ambiguity for risk-averse stakeholders, e.g., government contracts. Design exercise, managing a hospital expansion scenario, build a new hospital wing with strict regulatory deadlines and diverse stakeholders, doctors, patients, contractors. Steps, 1. Methodology choice, hybrid waterfall for regulatory approvals, agile for interior layout customization. 2. Stakeholder map, prioritize surgeons, high power, high interest, for design input. 3. Conflict plan, mediation protocol for disputes between architects and clinical staff. Emerging trends, AI-driven stakeholder analysis, tools like Stakeholder.ai predict concerns using NLP on emails and meeting notes. Virtual collaboration, metaverse platforms, e.g., NVIDIA Omniverse, enable immersive stakeholder reviews. Key takeaways for practitioners 1. Methodology fit, align agile/waterfall with project complexity and stakeholder appetite for change. 2. Proactive communication, over-communicate to preempt conflicts, silence breeds mistrust. 3. Conflict as opportunity, healthy debates can surface innovative solutions, e.g., SpaceX's iterative failure analysis. This section equips leaders to navigate methodology trade-offs and stakeholder dynamics, transforming potential chaos into coordinated success. By marrying structure with adaptability, projects can achieve both precision and resilience. Chapter 4, Management Strategies for Execution and Oversight 4.2 Tools for Operational Excellence. Operational excellence requires precision in planning, resource allocation, and risk mitigation. This section explores project scheduling software and budgeting/risk management frameworks that empower teams to deliver projects on time, within budget, and with minimal disruptions. Project scheduling software 1. Primavera P6, purpose, enterprise-level scheduling for complex projects, construction, aerospace, energy. Key features, critical path method, CPM identifies tasks that directly impact project timelines. Resource leveling, balances workforce and equipment allocation to avoid over-allocation. Scenario analysis, simulates delays or resource shortages to test contingency plans. Case study, Crossrail, London, challenge, coordinate 10,000 plus tasks across 40 stations and 26 miles of tunnel. Outcome, Primavera track dependencies and flagged bottlenecks, reducing delays by 15%. 2 Microsoft project, purpose, mid-sized project scheduling with user-friendly interfaces. Key features, Gantt charts, visualize timelines, dependencies, and milestones. Baseline comparisons, track progress against original plans. Integration, syncs with Power BI for real-time dashboards. Case study, Nike product launches, use case, managed global rollout timelines for limited edition sneakers. Outcome, reduced time to market by 20% via streamlined task assignments. Comparison feature Primavera P6 MS project scalability best for large, multi-phase projects, ideal for SMEs or departmental projects. Cost high, enterprise licensing, affordable, subscription-based, customization advanced, supports custom metrics, moderate, pre-built templates. Actionable tip, use Primavera for mega projects, e.g., dams, airports, and MS. Project for IT rollouts or marketing campaigns. Budgeting and risk management frameworks. 1. Budgeting frameworks, earned value management, EVM, metrics, planned value, PV budgeted cost of work scheduled. Earned value, EV budgeted cost of work performed. Actual cost, AC actual spend. Insights, cost performance index, CPIF/AC, CPI1 equals over budget. Schedule performance index, SPIF/PV, SPI1 equals behind schedule. Case study, NASA's Artemis program, EVM flagged at 12% cost overrun early, enabling corrective procurement strategies. Zero-based budgeting, ZBB, principle, justify every expense from scratch, rather than incremental adjustments. Example, Unilever saved $1.2 billion over 5 years by adopting ZBB. 2 Risk management frameworks, ISO 31000, steps, identify, analyze, evaluate, treat risks. Tool, risk matrices to prioritize threats by likelihood and impact. PMI's PMBOK risk management, process, plan, identify, perform qualitative/quantitative analysis, plan responses, monitor. Quantitative tools, Monte Carlo simulations, model costs/schedule uncertainties, e.g., 10,000 iterations. Decision trees, evaluate options based on risk/reward outcomes. Case study, BP Steepwater Horizon response, challenge, manage financial, reputational, and environmental risks post-spill. Framework, combined Monte Carlo simulations, cost liability, and stakeholder analysis, community trust. Outcome, $65 billion in managed liabilities and improved safety protocols. Integration of tools, scheduling and budgeting, link Primavera timelines to EVM in Excel for real-time cost tracking. Risk and budgeting, use Monte Carlo results to adjust contingency reserves, e.g., plus 15% budget for high-risk IT projects. Challenges and solutions, tool complexity, train teams via certifications, Oracle Primavera, PMP. Data silos, integrate tools via APIs, e.g., MS Project left and right arrow SAP. Resistance to ZBB, start with pilot departments to demonstrate ROI. Design exercise, renewable energy plant scenario, build a solar farm with a $50 million budget and 18-month deadline. Steps, 1. Schedule, use Primavera to map permitting, panel installation, and grid integration. 2. Budget, apply EVM to track panel procurement, PV equals $20 million, EV equals $18 million, AC equals $22 million, CPI equals 0.81. 3. Risk, run Monte Carlo simulations for supply chain delays, 10% probability of 3-month delay. Emerging trends, AI-driven scheduling, tools like Origo AI auto-adjust timelines based on weather or labor data. Real-time risk analytics, platforms like Riskalyze scan news and social media for emerging threats. Key takeaways for practitioners. 1. Tailored tools to project size, Primavera for scale, MS Project for agility. 2. Quantify risks early, use simulations to secure stakeholder buy-in for contingencies. 3. Align budgets with outcomes, EVM and ZBB prevent budget drift and foster accountability. This section equips teams to master the tools and frameworks that transform chaotic workflows into streamlined operations. By marrying precision with adaptability, organizations can achieve operational excellence even in the face of uncertainty. Chapter 4, Management Strategies for Execution and Oversight. 4.3 Case Studies in Management. This section examines real-world applications of management strategies through 2 lenses, megaproject management and crisis management in construction delays. These case studies highlight lessons learned, challenges overcome, and the critical role of adaptive leadership and robust frameworks. Case Study 1, Megaproject Management Lessons from Infrastructure Development Project, Crossrail, Elizabeth Line, London, UK. Overview, Objective, construct a 73-mile railway connecting London and the South East, with 42 km of new tunnel. Stakeholders, UK Government, Transport for London, TfL, contractors, e.g., Balfour Beatty, and the public. Original budget and timeline, £14.8 billion, scheduled completion in 2018. Challenges, 1. Technical complexity, tunneling under historic London with limited ground disturbance. 2. Stakeholder coordination, managing 40+ contractors and 10,000+ workers. 3. Regulatory hurdles, compliance with heritage and environmental regulations. 4. Delays and budget overruns, opened in 2022 with a final cost of £18.8 billion. Management strategies, integrated project delivery, IPD collaborative contracts incentivizing shared risk/reward. Primavera P6, tracked 500,000+ tasks to identify critical path delays. Stakeholder engagement, regular public consultations to mitigate community disruptions. Outcomes, successfully transported 200 million passengers by 2023. Lessons learned, contingency planning, allocate 15-20% budget buffers for unforeseen risks. Adaptive leadership, shift from waterfall to agile sprints for software systems. Transparency, publish quarterly progress reports to maintain public trust. Case Study 2, Crisis Management in Construction Delays Project, Berlin-Brandenburg Airport, Bur, Germany. Overview, Objective, replace Berlin's aging airports with a state-of-the-art hub. Original timeline and budget, €2.8 billion, opening in 2011. Actual outcome, opened in 2020 at €7 billion after 9 years of delays. Crisis triggers, 1. Planning failures, fire safety system defects and flawed terminal design. 2. Mismanagement, frequent leadership changes and lack of accountability. 3. Technical issues, over 120,000 construction defects identified. Crisis response strategies, restructuring, appointed a new CEO and independent oversight board. Root cause analysis, RCA audits revealed poor contractor coordination. Phased opening, prioritized critical systems, e.g., baggage handling, to avoid total failure. Outcomes, achieved partial operational capacity in 2020, with full functionality by 2022. Lessons learned, risk audits, conduct third-party reviews during planning phases. Communication protocols, establish crisis hotlines for real-time stakeholder updates. Modular design, implement scalable solutions to isolate delays, e.g., terminal sections. Cross-case insights 1. Tool integration, both projects relied on scheduling software, Primavera, but lacked real-time risk analytics. 2. Stakeholder trust, Crossrail's transparency contrasted with BIR's opacity, impacting public perception. 3. Adaptability, Crossrail's agile adjustments mitigated delays, while BIR's rigid planning exacerbated them. Design exercise, managing a high-speed rail megaproject scenario, a $20 billion rail project faces delays due to land acquisition disputes. Steps, 1. Stakeholder mapping, use a RACI matrix to clarify roles, e.g., local governments as accountable. 2. Crisis simulation, run Monte Carlo models to assess delay impacts on budgets. 3. Communication plan, deploy AI-driven dashboards for transparent progress tracking. Emerging trends, digital twins, virtual replicas for real-time megaproject monitoring, e.g., NEOM's The Line. Predictive crisis management, AI tools like Ditto forecast delays using weather and supply chain data. Key takeaways for practitioners 1. Proactive risk buffers, embed contingency reserves in budgets and timelines. 2. Leadership agility, pivot methodologies, e.g., hybrid agile waterfall, in response to crises. 3. Stakeholder synergy, align incentives across contractors, governments, and communities. This section underscores that effective management is not about avoiding crises but navigating them with foresight, flexibility, and accountability. By learning from past megaprojects and crises, leaders can turn challenges into opportunities for innovation and resilience. Chapter 5, Cross-disciplinary applications 5.1 Integrating design, analysis, construction, and management. This section explores how merging design, analysis, construction, and management through systems thinking and collaborative workflows drives innovation, efficiency, and resilience in complex projects. 1. Systems thinking in complex projects. Definition, a holistic approach that examines how project components, design, analysis, construction, management, interact within the broader system. Key principles, interdependency, recognize that design choices impact construction feasibility, cost analysis, and long-term management. Feedback loops, use iterative processes to refine solutions, e.g., post-occupancy evaluations informing future designs. Holistic optimization, balance competing priorities, cost, sustainability, aesthetics, for system-wide benefits. Example, smart city development, design, pedestrian-friendly urban layouts. Analysis, environmental impact assessments, noise, emissions. Construction, modular infrastructure for scalability. Management, IoT sensors for real-time traffic and energy monitoring. Case study, The High Line, New York City, integration, blended landscape architecture, design, ecological analysis, phased construction, and community engagement, management. Outcome, a resilient public space that reduced urban heat and boosted local economies. Benefits, sustainability, reduces waste by aligning design with life cycle analysis. Resilience, anticipates risks, e.g., climate impacts, through interconnected planning. 2. Collaborative workflows across disciplines. Definition, breaking down silos to enable seamless interaction between architects, engineers, contractors, and managers. Tools and methodologies, building information modeling, BIM shared 3D models for clash detection and resource tracking, e.g., Shanghai Tower, integrated project delivery, IPD contracts incentivizing shared risk/reward among stakeholders. Agile/Lean, sprints and Kanban boards to align cross-functional teams. Case study, Shanghai Tower, collaboration, architects, Gensler, engineers, TT, and contractors used BIM to resolve 5,000 plus clashes pre-construction. Outcome, completed 2 years faster than comparable skyscrapers, with 25% material savings. Benefits, efficiency, reduced rework and delays, e.g., Crossrail saved £1 billion via BIM coordination. Innovation, diverse perspectives yield creative solutions, e.g., Tesla's Gigafactory design. Challenges and solutions, resistance to change, train teams on collaborative tools, e.g., Autodesk Revit workshops. Conflicting priorities, align KPIs across disciplines, e.g., shared bonuses for on-time delivery. 3. Overcoming integration challenges strategies, communication, daily stand-ups, digital dashboards, e.g., Procore and common data environments, CDEs. Leadership, foster a culture of transparency and accountability, e.g., BIM champions. Phased adoption, pilot collaborative tools on small projects to demonstrate ROI. 4. Future trends, AI-driven systems analysis, tools like digital twins simulate real-time performance, e.g., Singapore's Virtual Singapore. Generative design, algorithms optimize structures for cost, carbon, and constructability, e.g., Autodesk's Dreamcatcher. Blockchain, secures shared data in collaborative workflows, e.g., smart contracts for IPD. Key takeaways. 1. Systems thinking transforms isolated tasks into cohesive strategies, enhancing sustainability and adaptability. 2. Collaborative workflows break silos, accelerating delivery and reducing costs through tools like BIM and Agile. 3. Leadership and culture are critical to overcoming resistance and fostering innovation. By integrating design, analysis, construction, and management, projects can transcend traditional limitations, achieving outcomes that are as efficient as they are visionary. Chapter 5, Cross-Disciplinary Applications 5.2 Emerging Trends and Innovations. This section explores cutting-edge advancements reshaping design, construction, and management, focusing on AI-driven predictive analysis and circular economy principles. These innovations foster efficiency, sustainability, and resilience in modern projects. 1. AI and Machine Learning in Predictive Analysis. Introduction. AI and Machine Learning, ML, leverage historical data and real-time inputs to forecast outcomes, optimize workflows, and mitigate risks. These tools are revolutionizing decision-making across project life cycles. Applications. 1. Design, generative design, AI algorithms, e.g., Autodesk's Dreamcatcher, generate optimized designs based on constraints like material use and cost. Performance simulation, ML models predict energy efficiency, structural integrity, and occupant comfort. 2. Construction, delay prediction, tools like Alice Technologies analyze weather, labor, and supply chain data to forecast bottlenecks. Resource optimization, AI schedules equipment and labor to minimize idle time, e.g., Doxal's progress tracking via drones. 3. Management, risk assessment, platforms like Nplan use historical data to quantify project risks. Predictive maintenance, IoT sensors paired with ML predict equipment failures, e.g., Siemens MindSphere. Case study, Smart Bridge Monitoring, Project, AI-powered sensors on the Millau Viaduct, France, predict wear and tear, enabling proactive repairs and extending lifespan. Outcome, reduced maintenance costs by 25% and avoided unplanned downtime. Challenges and future directions, data privacy, secure cloud solutions, e.g., Microsoft Azure, encrypt sensitive project data. Integration, bridging AI tools with legacy systems remains a hurdle. Future trends, autonomous construction robots, e.g., build robotics, and AI-driven urban planning. 2. Circular economy principles in design and construction. Introduction. The circular economy shifts from a linear take-make-waste model to closed-loop systems prioritizing reuse, recycling, and regeneration. Key principles. 1. Design for disassembly, DFD modular components, e.g., Google's Project Era, enable easy upgrades and recycling. 2. Material innovation, self-healing concrete, microorganisms repair cracks, e.g., biomason. Biodegradable insulation, mycelium-based materials replace synthetic foams. 3. Waste minimization, material passports, digital records, e.g., Modester, track components for future reuse. Prefabrication, factories cut on-site waste by 90%, e.g., Catera. Case study, the Circular Building, London, project, a prototype using 100% reusable materials, including leased carpet tiles and modular walls. Outcome, zero waste to landfill and 60% lower embodied carbon. Challenges and future directions, cost barriers, higher upfront costs offset by long-term savings, e.g., interfaces recycled carpet tiles. Regulatory gaps, policies like the EU's Circular Economy Action Plan drive adoption. Future trends, blockchain for material tracking and AI-optimized recycling workflows. Synergies between AI and circular economy, AI-driven material sorting, robots like ZenRobotics separate recyclables with 95% accuracy. Life cycle analysis, ML models evaluate designs for circularity, e.g., Tally for Revit. Key takeaways. 1. AI/ML transforms industries through predictive insights, reducing costs and enhancing safety. 2. Circular economy principles minimize waste and carbon footprints, aligning with global sustainability goals. 3. Integration, combining AI with circular strategies unlocks systemic efficiencies, e.g., smart material reuse. These trends are not just technological leaps but essential responses to climate and resource challenges. By embracing AI and circularity, industries can build smarter, greener, and more resilient futures. Chapter 5, Cross-Disciplinary Applications. 5.3 Global Perspectives. Global projects demand navigating cultural diversity, regulatory complexity, and geopolitical dynamics. This section examines challenges in international collaboration and highlights strategies for success through a case study of cross-border infrastructure development. Cultural and regulatory challenges in international projects. 1. Cultural challenges, communication styles, direct versus indirect. German engineers may prioritize explicit feedback, while Japanese teams often favor consensus-driven communication. Hierarchy, flat organizational structures, e.g., Scandinavian firms, versus rigid hierarchies, e.g., Middle Eastern governments. Work ethic norms, time perception, flexible deadlines in Southern Europe versus strict punctuality in Singapore. Risk tolerance, Silicon Valley's fail-fast ethos versus risk-averse cultures in legacy industries. Mitigation strategies, cultural training, workshops on local customs and negotiation tactics. Liaison roles, hire bilingual project managers to bridge gaps, e.g., Bechtel's use of cultural mediators in Saudi Arabia. 2. Regulatory challenges, divergent standards, safety codes, EU CE marking versus China CCC certification. Environmental laws, stricter emissions rules in the EU versus developing nations with lax enforcement. Political risks, sanctions, sudden trade restrictions, e.g., Russia-Ukraine conflict disrupting supply chains. Local content requirements, mandates to hire local labor or source materials, e.g., Nigeria's Oil and Gas Industry Content Development Act. Mitigation strategies, regulatory audits, partner with local legal experts to map compliance requirements. Modular contracts, segment projects to isolate geopolitical risks, e.g., phased approvals. Case study, Cross-Border Infrastructure Development Project, Resund Bridge, Denmark Sweden, Overview, a 16 km rail/road bridge tunnel connecting Copenhagen, Denmark, and Malmö, Sweden. Challenges. 1. Cultural differences, design priorities, Danish focus on minimalist aesthetics versus Swedish emphasis on functional durability. Labor practices, Swedish unions demanded co-determination rights, unfamiliar to Danish contractors. 2 regulatory hurdles, environmental laws, stricter Danish noise pollution standards versus Sweden's biodiversity protections. Taxation, VAT discrepancies between EU, Denmark, and non-EU, Sweden at the time, entities. 3 technical coordination, metric versus imperial, Sweden used metric, Danish subcontractors occasionally defaulted to imperial. Strategies for success, joint governance, a binational authority, Resunsbro-koncertet, streamlined approvals. Hybrid design, merged Danish aesthetics with Swedish modular engineering, precast tunnel segments. Stakeholder engagement, public forums addressed concerns, e.g., fishermen worried about disrupted currents. Outcomes, completed in 2000, 1 year ahead of schedule and 10% under budget. Boosted cross-border GDP by €1.5 billion annually via enhanced trade and tourism. Won the IOBS Outstanding Structure Award for Technical and Cultural Integration. Cross-case insights 1. Shared governance, binational projects thrive with neutral oversight bodies, e.g., Channel Tunnels Intergovernmental Commission. 2. Local adaptation, align designs with cultural identities, e.g., Hong Kong Zhuhai Macau Bridge incorporated Feng Shui principles. 3. Risk buffers, allocate 15-20% budgets for unforeseen regulatory shifts. Design exercise, cross-border rail project in Africa scenario, connect Nairobi, Kenya, to Kampala, Uganda, amid varying gauges and customs protocols. Steps, 1. Cultural audit, map tribal land rights and labor practices. 2. Regulatory alignment, harmonize safety standards via the East African Community, EAC. 3. Modular design, use adjustable track gauges to accommodate future expansions. Emerging trends, digital collaboration, metaverse platforms, e.g., NVIDIA Omniverse, enable real-time 3D reviews across time zones. Blockchain for compliance, smart contracts automate customs and tax payments, e.g., Maersk Stratelands. Geopolitical risk tech, tools like Prism forecast political instability using AI. Key takeaways for practitioners 1. Cultural intelligence, invest in cross-cultural training and local partnerships. 2. Regulatory agility, design modular systems that adapt to legal shifts, e.g., adjustable emissions controls. 3. Diplomatic engagement, treat governments as partners, not obstacles, e.g., CO funding models. This section underscores that global projects are as much about managing people and policies as they are about engineering. By embracing cultural diversity and regulatory nuance, teams can turn cross-border challenges into opportunities for innovation and unity. Conclusion: the journey through applying practical principles in design, analysis, construction, and management has illuminated the interconnected pillars of modern industry. From foundational design tenets to cross-border megaprojects, this book underscores that success lies not in isolated expertise but in the synthesis of disciplines, foresight, and adaptability. Here, we distill key insights and chart a path forward. Synthesizing practical principles for future challenges. 1. Interdisciplinary integration, design, analysis, construction, and management are not siloed phases but a cohesive workflow. For instance, the High Line, NYC, merged ecological analysis with community-centric design, while agile construction and stakeholder management ensured its enduring impact. Systems thinking bridges gaps. A building's energy efficiency design hinges on life cycle assessments, analysis, modular techniques, construction, and IoT-driven maintenance management. 2. Sustainability as a non-negotiable. Projects like Bosco Verticale, Milan, and the Circular Building, London, prove that circular economy principles reuse, recycle, regenerate are both ecologically vital and economically viable. 3. Resilience through technology, tools such as BIM, AI-driven predictive analytics, and digital twins transform uncertainty into actionable insights. The Millau Viaduct exemplifies how AI-powered monitoring extends infrastructure longevity. 4. Global cultural nuance, cross-border ventures like the Resund Bridge thrive when cultural intelligence and regulatory agility are prioritized. Shared governance and hybrid designs turn geopolitical complexity into collaborative triumph. The role of continuous learning and adaptation. 1. Embracing disruption, the rise of AI, 3D printing, and blockchain demands perpetual upskilling. Professionals must evolve from static expertise to dynamic problem solving, as seen in Tesla's gigafactories, where lean manufacturing meets machine learning. 2. Agility in crisis, lessons from Berlin-Brandenburg Airport and Crossrail reveal that rigid methodologies fail. Adaptive frameworks, e.g., hybrid agile waterfall, and transparent communication salvage stalled projects. 3. Anticipating tomorrow's challenges, climate change, urbanization, and digital transformation will redefine industries. Modular designs, predictive risk models, and decentralized systems, e.g., smart grids, will be critical. A call to action. The future belongs to those who view principles not as rigid rules but as living tools. As Buckminster Fuller urged, you never change things by fighting the existing reality. To change something, build a new model that makes the existing model obsolete. For practitioners, apply these principles, but iterate relentlessly. Pilot AI tools, advocate for circular materials, and engage diverse stakeholders. For leaders, foster cultures of curiosity, invest in training, reward innovation, and dismantle silos. For visionaries, champion systemic change. The next Resund Bridge or High Line awaits those bold enough to reimagine boundaries. In closing, the principles within this book are a compass, not a destination. As industries evolve, so must we, learning, adapting, and building a world where efficiency, sustainability, and humanity coexist. The blueprint is here, the future is yours to construct. Appendices. Appendix A, Glossary of Key Terms. 1. Agile methodology, an iterative project management approach emphasizing flexibility, collaboration, and customer feedback through incremental deliverables. 2. BIM, building information modeling, a 3D model-based process for designing, constructing, and managing buildings with real-time data integration. 3. Circular economy, an economic system prioritizing reuse, recycling, and regeneration to minimize waste and resource consumption. 4. Critical path method, CPMA project scheduling algorithm identifying tasks essential to meeting deadlines. 5. Digital twin, a virtual replica of a physical asset or system used for simulation, monitoring, and optimization. 6. Earned value management, EVMA budgeting tool tracking project performance against cost and schedule baselines. 7. FIA, finite element analysis, a computational method for predicting structural behavior under stress, heat, or vibration. 8. Human-centered design, HCDA design framework prioritizing end-user needs and feedback. 9. ISO 31000, an international standard for risk management principles and guidelines. 10. Life cycle assessment, LCA, a method evaluating environmental impacts of a product or system from raw material extraction to disposal. 11. Monte Carlo simulation, a statistical technique modeling project risks using thousands of probabilistic scenarios. 12. Prefabrication, manufacturing building components off-site for rapid on-site assembly. 13. SWOT analysis, a strategic tool assessing strengths, weaknesses, opportunities, and threats. 14. Value engineering, a systematic approach to optimizing cost, quality, and functionality. Appendix B, templates for project planning and risk assessment. 1. Project planning template section details project overview, objective, brief description. BR, stakeholders, list key parties. Phases. 1. Phase 1 name, tasks, timeline, deliverables. BR2. Phase 2 name, timeline Gantt chart or table with milestones, start/end dates, dependencies. Resources, labor, roles/FTEs BR, materials, list BR, budget, allocation risk register link to Appendix B2. 2. Risk assessment template risk ID risk description likelihood, low/med/high, impact, low/med/high, mitigation strategy owner -R1 e.g., supply chain delays high diversify suppliers procurement team R2 e.g., regulatory changes medium monitor policy updates legal department Appendix C, further reading and resources books and articles 1. The Lean Startup by Eric Ries Agile Principles for Innovation. 2. Cradle to Cradle, Remaking the Way We Make Things by William McDonough Circular Economy Foundations. 3. Project Management Body of Knowledge, Bach Registered Trademark Guide, PMI's Global Standard for Project Management. 4. AI in Construction, From Design to Maintenance, Journal of Construction Engineering, 2023. Online resources 1. Autodesk University, free courses on BIM, CAD, and generative design. 2. ISO Standards Portal, access ISO 31000 and other frameworks. 3. Circular Economy Toolkit, circularity.tools, https://circularity.tools, Guides for Sustainable Design. Tools and Software 1. Primavera P6, Enterprise Project Scheduling. 2. Tally Registered Trademark, Revit Plugin for Life Cycle Assessments. 3. NPlan, AI-driven risk prediction for construction. Certifications 1. PMP, Project Management Professional PMI's globally recognized credential. 2. Lead AP, Accredited Professional Green Building Certification. 3. Certified Scrum Master Registered Trademark, Agile Methodology Training. Professional Organizations 1. Project Management Institute, PMI Networking and Certifications. 2. Royal Institute of British Architects, RIBA Sustainable Design Resources. 3. International Living Future Institute, ILFI Advocacy for Regenerative Design. These appendices equip readers with practical tools, definitions, and resources to implement the principles discussed in the book. Use the templates as starting points, refine the glossary for team alignment, and leverage further reading to deepen expertise.